This is Mrs. O'Neill for AP Chemistry, Chapter 20, Section 4, Cell Potentials Under Standard Conditions. In this section, you're going to see that an important characteristic of voltaic cell is its cell potential, which is the difference in the electric potentials at the two electrodes and is measured in units of volts. So we're going to also know that half cell potentials are tabulated for reduction half reactions under standard conditions. That's why they're called standard reduction potentials. So at this point, pause the video, fill in the notes, and then play to hear my words. So the cell potential between the two electrodes is the difference between them. Hence subtraction. I also want to show you or bring back that Coulomb's guy. One electron is going to equal 1.6 times 10 to the negative 19 coulombs, and this is going to be our electromotive force. Okay, it's measured with a voltmeter, and of course our units is in volts. So we want to remember that a positive cell potential means that a spontaneous reaction is going to occur. So if we have positive volts, the reaction is going to happen spontaneously. So give it some thought, pause, and can you answer this? Hopefully that makes sense. So what is standard cell potential? Well, again, that's where that little circle above there comes into play. Just like we saw before, that little circle meant like the formation under standard conditions. So in other words, we call these cells redox reactions. Well, redox reactions means that you have two half reactions. So you have to combine those two half reactions to get what's called the standard cell potential of the total overall reaction. So standard reduction potentials are giving you a list. Okay, they're going to give you a list, and that list is going to be, which I'll show you in a minute, a list of reduction half reactions. So what we're going to do is cathode minus anode, or reduction minus oxidation, or products minus reactants. So again, give this some thought. Could you come up with that? Hopefully that makes sense, because we've talked about gases being at 1 atmosphere for standard conditions, and of course aqueous means 1 molar. So we can do one of many things to figure out the cell potential of our overall reaction. Cathode minus anode. Or if they're talking about a cell diagram, it's usually right minus left, but we still want to remember in which way those electrons are moving. And of course, reduction minus oxidation. I like this one, reduction minus oxidation, because it's like the word redox. These electrochemistry reactions are really a redox reaction, so it's going to be the reduction guy minus the oxidation guy. But we just need to know what that means. So we can do it that way, or what's going to happen is the list that they give us is a list of reduction reactions, which means the oxidation reaction, we gotta flip its charge and then we just add them. Okay, so again, we're either doing some subtraction or we're reversing the value or the sign of the oxidized guy and then adding the two. Does the same thing, just letting you know. So if we look at something like this, again, a reaction diagram, pause, see if you can kind of figure out what's going on, and then does this make sense? Your R is up here because your electrons is a reactant. So this is going to be your R, the R is the reactant, electrons are as reactants here, right? And then of course your O as product, your electrons are here at the product side. So what's happening here is your product, right? Your product, your cathode is minusing your reactant, product minus reactant. So it's different ways of just thinking about things, right? So again, your reduction, I'm sorry, the R here is really for reduction, right? What's happening here is reduction, the electron as a reactant. Here, the oxidation part, the electrons is the product. So again, something to think about, product minus reactant, okay? And then you get your value. So again, this reduction potential list that I'm going to show you in a minute, the more positive your voltage, the more easily that substance or that element is going to be reduced. So obviously the opposite is going to happen the other way. So this is the list I'm talking about. So they have to give you some kind of list. And that list is, again, always in the reduction half reaction. How do I know that? All of the electrons are on the reactant side. So we know that these are all listed as reduction half reactions. And it also says reduction potentials. So notice the top of the list, he's going to be the most easily reduced. And if we go to the bottom of the list, and this should really make sense, lithium really doesn't like to be reduced. Lithium likes to be oxidized. Number one, he's a metal. So all of these below hydrogen, which is our, standard, our starting point. We always have to have somewhere there's a zero, right? Everything has to relate back to zero so we can kind of have numbers above and below it. So if we have hydrogen as our standard, everything above it is getting easier to be reduced, and everything below it is going to be easy to be oxidized. And this should make sense because lithium is very, very, very reactive, right? It's one of those metals that even has to be stored in oil because it is so reactive with the air. Well, why is it so reactive with the air? Well, because again, it is so reactive, it really, really, really wants to be oxidized. And that's why, look at the value even, right? -3 versus up here, +2.8. Okay, so they have to give you this list and they have to give you those E values. So let's look at an example. Here's a redox reaction going on, right, in electrochem. They're giving us the half reactions and the E values that go along. But again, we need to remember that they're giving us the reaction as reduction. Well, one of these has got to be oxidized. Ooh, that box again. Which one's getting bigger in charge? Which one's getting oxidized? So again, our E cell, our equation we're going to use is cathode minus anode, or reduction minus oxidation, or products minus reactant. So the silver is being reduced and the copper is being oxidized. Hopefully you can figure that out. So with the cathode, I'm going to take that silver and I'm going to now multiply it by 2 though. Why do I have to multiply it by 2? Because I got to get rid of these electrons. Remember, I don't see any electrons in our overall reaction, right? Those electrons better be canceled out. So I have to multiply by 2. But notice my E value stays the same. Just because we multiplied it by 2 does not change the E value. And the copper is going to be flipped. So we're going to flip our anode, or our oxidation reaction, because again, we need to cancel out those electrons. Now this time what I did was I kept that E value the same because I'm going to use the cathode minus anode. So our overall reaction, we add everything up on the left, add everything up on the right, and we can cancel out those electrons. So we need to do cathode minus anode. So the 0.8 minus the 0.3 give us a positive 0.46 volts, which means this is going to be a spontaneous reaction if we build a cell in this way. Okay, now just as a reminder, you could always have just made this a negative 0.34 and then of course add them up. It's the same thing, right? 0.8 minus 0.34 would have been the same thing. So can you do this one? Can you pause the video and see if you can figure out how to get the cell voltage of this reaction? Hopefully you figured that out. Hopefully you knew to multiply the iron by 2 because we need to get rid of those electrons, but the voltage stays the same. Hopefully you knew to reverse the copper again because the copper is easier to be oxidized than it is to be reduced. So again, our left side versus our right side, and we can cancel out those electrons. And now we do the math. 0.77 minus 0.34, again, a positive 0.43 volts gives us a spontaneous reaction. So the strength of those oxidation and reducing agents is, again, think about what's being oxidized, what's being reduced, and then the opposite for the agents. So if we look at this again, easily being reduced, easily being oxidized. Okay, so it's just again, another visual to give you, and this should make sense. Lithium is really, really reactive metal. It's going to want to be oxidized, and iron is a non-metal. And think about, I'm sorry, fluorine, I'm sorry. Fluorine is a non-metal. Remember, fluorine is very, very reactive as a non-metal, and it wants electrons, right? Because it's a really high electronegativity. Okay, so that's what's going to happen there. Okay, see you in class.